Welcome back. If you are joining me from the colder countries at this time, you are likely in a warm room. Or if you're joining me from a warm country, you could be in an air-conditioned room at this moment. And if it's early in the morning, it may be that you are sipping on a delicious cup of coffee to start the day. For the heating or cooling of your room and the heating of water or milk for that cup of coffee, energy is required. Hereby, a distinction can be made between the final energy use and the primary energy use. This lecture will address this distinction. A nice way to discuss the concept of primary energy and the final energy use is by relating it to our energy system. We will discuss the energy system that can be seen as a whole of 5 sequential activities. The learning objectives of this video lecture are: first, understand what are the essential processes that define an energy system. Secondly, being able to distinguish between the primary energy and the final energy use. Thirdly, how is the energy efficiency of an energy system defined? And lastly, understanding a Sankey diagram that represents the processes and flows of energy carriers in an energy system. As mentioned, our energy system can be seen as a whole of 5 sequential activities, being winning of energy, conversion of energy into other forms, transport of the energy, storage and distribution of the energy, the conversion of energy in a usable form at the end user, and the functional end use itself. First of all, you have the winning of energy. This can take place through energy carriers such as coal, oil, or natural gas extracted from the earth. The chemical energy contained within these energy carriers can be categorized as primary energy. Primary energy is thus the energy found in its original or natural form. In addition, primary energy can also be extracted from resources such as wind, the sun, and water. But hey, we can't do much with crude oil, right? The next step is conversion, where the primary energy is converted into secondary energy, which is contained in energy carriers for which our society is designed. The most important energy carrier is electricity, and this conversion takes place in power plants. In the conversion from primary to secondary energy, large losses typically occur. For example, in a coal power plant, a conversion efficiency of 40% is common. Remember, in the previous video we have defined efficiency as the ratio of useful energy output to the total energy output. This means that for 40 joules of electricity, 100 joules of chemical energy in the form of coal is needed. Now this energy has to go from the plant to the consumers, right? The next step of transportation, distribution, and storage takes care of this function. When taking the example of electricity, this electricity is transported over the national high voltage lines, to the regional mid voltage lines, then to the low voltage lines in your neighborhood, and finally towards your home. Also in this step, some electrical transport losses occur, like conductor resistance losses, corona discharges, capacity losses, and inductive losses, and transformer losses from one voltage level to another. For electricity transport, an efficiency of 95% can be assumed. The storage step for electricity is more challenging than, for instance, compared to oil, for which storage is more practical. The next step of final conversion and end use takes place at the user such as you. This I will elaborate with an example. For this example, we go back to that cup of coffee you may be drinking right now. As mentioned before, you heated up water or milk for the cup of coffee in, let's assume, an electric coffee machine. During this process, the secondary energy contained in electricity is converted into heat, which is then transferred to your coffee, heating it up. Now assuming your coffee machine has an energy efficiency of 80%, a very modern boiler. This means that 80% of the energy input to your coffee machine is actually used to heat up your milk or water as useful energy. The remaining 20% of the energy input escapes the machine as heat or goes into the heating of the cup itself. Now, to heat 350 milliliters of water to, let's say, 80 degrees Celsius in 3.5 minutes, the theoretical required amount of useful energy needed is 33.9 watt hours, or in other words, a power of 580 watts for 3.5 minutes, which is equal to 0.0583 hours. This means that for the coffee machine with an efficiency of 80%, the total energy input of electricity equals to 40.7 watt hours, or expressed in power is 720 watt for 3.5 minutes. The 47 watt hours of energy required for the conversion at home is what we call the final energy use. The useful energy use can thus be defined as the energy we actually and effectively use to conduct our activities and fulfill our needs. We can analyze the entire chain efficiency from the primary energy in coal all the way to the useful energy used by multiplying the efficiency per sector or process step of the energy chain. If we collect the data from this lecture, we get the following. A winning efficiency of 95% as losses occur and energy is required for transportation and processes of the resources. A conversion efficiency of 40%, transportation efficiency of 95%, and finally the boiler efficiency of 80%. For this case, the overall efficiency from primary energy use to useful energy use is 30%. For a simple process like making coffee, the energy loss is thus significant, and you may think we are very inefficient, which is true. But it can get even worse. For example, boiling an egg has an overall chain efficiency of 2%. You may ask yourself why this loss is so large and how we can improve this. However, a 100% conversion rate from primary energy to useful energy use is impossible. Thermal processes, such as the conversion from energy in coal to electricity, are bounded to a theoretical maximum conversion efficiency called the Carnot efficiency. We will come back in the course to the Carnot efficiency. However, in the past years, strong technological advances have been made which have increased the efficiency of power plants, reduced the power losses during transportation, and improved the efficiency of industrial machines and home appliances. With this said, I hope you can also contribute in improving our energy efficiency in the future. Here I show a visual representation of the real energy system of the European Union in the year of 2023 in a so-called Sankey diagram. It shows the winning, conversion, storage, transport and distribution, and end use of the energy carriers in the entire energy system. I will discuss it in the second part of this video lectures on energy systems, so see you in the next video.